We already have a lot of experience with geometric series. For example, if I have the infinite geometric series starting at n equals k to infinity of r to the n, which would be r to the k plus r to the k plus 1 plus r to the k plus 2, and keep going on and on and on forever. There's a few things we've already thought about here. We know what the common ratio is. So the common ratio, which is the ratio between consecutive terms, is going to be r to the k plus 1. Actually, let me just write this as r to the n plus 1. I don't want to fixate on this k right over here. So r to the n plus 1 over r to the n, well, this is just going to be equal to r. Anything to the n plus 1 over that same thing to the n, that's just going to be equal to r, or r to the first power. And you see that here. When you go from one term to another, you are just multiplying by r. And this is all review. If it's not review, I encourage you to watch the videos on geometric series. And what's interesting about this is we've proven to ourselves in the videos on geometric series that if the common ratio, if the absolute value of the common ratio is less than 1, then the series converges. And if the absolute value of r is greater than or equal to 1, then the series diverges. And that made sense. We've proven it as well. But it also makes logical sense that, look, if the absolute value of r is less than 1, then each term here is going to go down by that common, or it's going to be multiplied by that common ratio, and it's going to decrease on and on and on and on and on. And so it makes sense that even though this is an infinite sum, it will converge to a finite value. Now, with that out of the way for review, let's tackle something a little bit more interesting. Let's say that we want to figure out whether a series like this, so starting with n equals 5 to infinity of, let's say, n to the 10th power, the numerator is growing quickly, n to the 10th power over n factorial. And factorial, we know, also grows very, very quickly. Probably it actually grows much faster than even a high degree polynomial like this, or a high degree term like this. But how do we prove that it converges? We could definitely use the divergence test to show that this does not diverge. But how do we prove that this actually converges? And maybe we can use a little bit of our intuition here. Well, let's see if we can come up with a common ratio. So let's see if there's a common ratio here. So let's take the n plus 1th term, which is going to be n plus 1 to the 10th power over n plus 1 factorial, and divide that by the nth term. So let's divide that by n to the 10th over n factorial. Well, dividing by a fraction, or dividing by anything, is equivalent to multiplying by its reciprocal. So let's just multiply by the reciprocal. So times n factorial over n to the 10th. Remember, all I'm trying to do is exactly what we did right over here. See if there's some type of a common ratio. Well, if we do a little algebra here, n plus 1 factorial, and factorial algebra is always fun. This is the same thing as n plus 1 times n factorial times n factorial. And you're not used to seeing order of operations dealing with factorial, but this factorial only applies to this n right over here. And why is that useful? Because this n factorial cancels with that n factorial. And we're left with n plus 1 to the 10th power over n plus 1 times n to the 10th times n to the 10th. So I know what you're thinking. Hey, wait, look, this isn't a fixed common ratio here. The ratio between consecutive terms here, when I took the n plus 1th term divided by the nth term, it's changing depending on what my n is. This ratio, I guess you could say, is a function of n. So this doesn't seem too useful. But what if I were to say, okay, well, look, in any of these series, we really care about the behavior as our n's get really, 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 really large, the limit as our n's go to infinity. So what if we were to look at the behavior here, and if this is approaching some actual value as n approaches infinity, well, it would make conceptual sense that we could kind of think of that as the limit of our common ratio. So let's do that. So let's take the limit as n approaches infinity of this thing. So remember what we're doing here. This isn't just kind of some voodoo. Conceptually, so let me copy and paste this. Conceptually, we're just trying to think about, well, what is the common ratio approach? What is the ratio between consecutive terms, the n plus 1th term and the nth term, as n gets really, 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 really large? And what we see here is we have this up here. We don't have to multiply it out. This is going to be n to the 10th plus a bunch of other stuff. It's going to be a 10th degree polynomial. And this down here, this is going to be, actually this one we can figure it out. This is going to be n to the 11th plus n to the 10th power. So the limit as n approaches infinity, well, this denominator is going to grow faster than that. You could divide the numerator and denominator by n to the 10th, and everything, well, you could divide actually the numerator and denominator by n to the 11th, and everything up here is going to go to 0, and this is going to be 1. And so the limit right over here is the limit, this limit is going to be equal to, this limit is going to be equal to 0. As n approaches infinity, one way, the ratio between consecutive terms approaches 0. So this seems, if we use the logic from our common ratio up here when we looked at geometric series, this is clearly not a geometric series, but it would say, well, look, as n gets really, really, really large, the ratio between consecutive terms gets smaller and smaller and smaller. Hey, maybe we can make the same conclusion. Maybe we can make the same conclusion that therefore the series actually converges. The series actually converges. So, or n factorial converges. So can we make this statement? And the answer is yes, we can. And what allows us to do it is the ratio test. So let me write that down. The ratio test. And all the ratio test tells us is if we have an infinite series, and I can say from n equals k to infinity, and if we take the limit as n approaches infinity, of the absolute value of a to the n plus 1 over a to the n, and over here I didn't take the absolute value of that limit, but we absolutely could have taken the absolute value of that limit. And all of these terms right over here were positive, so the absolute value would be the same thing as itself. If this approaches some limit, so once again, this limit is what is going to be our ratio between consecutive terms as n gets larger and larger. The ratio tells us if L is less than 1, which was the situation here, L is clearly less than 1, then the series converges. Series converges. Some definitions just say it's absolutely convergent. It will convert absolutely. The absolute value of the series converges, but then that also means that the series itself converges. If L is greater than 1, series diverges. And if L is equal to 1, it's inconclusive. We don't know. We would have to do some other test to prove whether it converges or diverges. So that's the essence of the ratio test. Find the absolute value of the ratio between consecutive terms. Take the limit as that n approaches infinity. If that approaches an actual limit, and that limit is less than 1, then the series converges. And it's really based on the same fundamental idea that we saw with the common ratio of geometric series.